Let me continue with the methodology. So we do initial calculations and use response theory, which we can do for several quantities. This is for any sign effect we have induced spin here, but it can also be induced orbital polarization. We have tensor here, which you can call it Rasper-Edelstein tensor or magnetoelectric susceptibility, and here the orbital magnetoelectric susceptibility. And these equations for response theory, you can directly derive them. We have in here, this is the momentum operator, but then the capital A operator will be spin operator or orbital operator or something else. I have to say, with connection to some of the things that were already mentioned in the first talk, we take the operators within the atomic sphere. So that is for the spin and orbital operators. And in general, if you look at the equations, there are two contributions. One is, you can call this interband, and it's not equal to m, and then you can also the intraband term, where we have to rewrite this, and we have that the part that comes from the Fermi surface. Okay, so this we have implemented in mean to K, and we can run the calculation for different materials, which I will show in a moment. And we can, of course, also look at spin Hall effect or the orbital Hall effect, and where the operator is then a little bit different. Of course, there are still the two lifetime quantities that we have to take into account. I will show that later on how they depend on the lifetimes. We do not take into account what is called extrinsic effects, such as side thread or scattering. And once we have this here, these quantities calculated, we can also go to the thermal effects, because they are given also by the response theory expression, where we have then, if it is orthogonal, we have the Nernst effect, but it can be due to the spin or it can be due to the orbital conductivity. Okay, so let us look at an example. Spin of the orbital Hall effect for 40 elements that we calculated, and here this part here. This is the 3D series, the 4D series, the 5D series. This is what we get. And you see actually what has been mentioned many times, and also was in this very nice paper by Tamara et al. The orbital Hall effect does not depend on the spin orbit, so we have actually very large orbital Hall effects for light metals. It was part of the motivation of the work that was presented before me. And they are of the same size, so we can actually go to light elements for orbital transport. So that is a very nice implication. If you go into the details, then you see actually only 3D elements are good, 4D or 5D, if I have here, for instance, aluminium, which is the light elements, but not the large orbital Hall effect. You can also compare to the calculations of Orbital. Then you can see here, this fits precisely also the size. Here we are at 9, so that in perfect agreement. However, if you go to Tamara et al, the first paper where the orbital Hall effect was reported for many elements. If you look at the green curve here, you see actually it goes down. We don't find that. Now it is large, but it does not have this shape that was predicted by Tamara et al, and actually it is also different. 5D series. So there are still details of the calculation that can be important. There's also a factor of 2 because they have a value 4, so we have 8. Okay, so what we see is that for the light metal, we have a very large orbital Hall effects. And we can now continue just for an example. We can look at the orbital effect by doing what is called the model expression that was on the transparency spec. And what you see then, this is again 40 elements here. Nice is now that here, if we take non-magnetic nickel, so we predict a very large orbital Nernst effect of diagonal, so a transfer thermal effect for nickel, and also palladium and platinum, they are quite large. The things that we have found in our calculations is that there is always a cluster of effects. And this is maybe a little bit new because we have seen now the spin Hall effect and the orbital Hall effect. But if you do these calculations as we were trying to do it, you find out every time there is a cluster of 4 effects that you can call spin Hall effect, orbital Hall effect, then there's the magnetic spin Hall effect and the magnetic orbital Hall effect. The same thing happens if you go to the Raspberry-Einstein effect. You have the spin Raspberry-Einstein effect, orbital Raspberry-Einstein effect, and then you have the magnetic components. And this again happens also if you go to the Nernst effect. Spin, Nernst, orbital Nernst, and then we have magnetic spin Nernst, magnetic orbital Nernst effects. And actually, if you look at it, so this, the top line here, this is an effect that is time reversal even. So that is given by a certain effect, I will come to it in a moment. These here, they are all time reversal off. So these are kind of new effects that have not been taken into account. And I want to highlight especially these new effects in my talk. So if you go back here and we look at the whole effect, so we have here the spin Hall effect, time reversal even, the spin Raspberry-Einstein effect, and also spin Nernst effect, all time reversal even, but not these lower lines here. And you can also make a plot here for how these things arise. The orbital Hall effect, you don't need spin orbit interaction. Those magnetic effects, you actually, they are off, but they require a form of magnetism. And what is also interesting is that actually these magnetic effects, they depend on what is the Fermi surface turn, and not from the very curvature turn. Okay, so we discovered actually these effects by doing after initial calculations. So the usual spin and orbital currents, they form a convention for the spin Hall effect. The spin current and the electric field and the spin polarization, they are all normal to each other. And they are time reversal even, as I already said, and you can calculate this often on this very curvature expression. So important is here this n is not equal to m. Now, if you go to these other effects, the anomalous effects, they actually have another convention. So when I have the spin current going in this direction, the electric field in this direction, but then the spin polarization is parallel to the electric field. So it does not follow this convention, but it is different. And these effects, they are time reversal off. So, and actually they are not given by the Fermi, by the Berry curvature, but they are given by the Fermi surface. So n must be n. And we did so actually we discovered this effect, and it turns out that these effects, magnetic spin Hall effect, magnetic orbital Hall effect, it is always there when you have a magnetic. Question is if it is larger or smaller than spin Hall effect. But it is always there, and it has actually a different polarization. Now, so the normal spin Hall effect points in this direction, magnetic spin Hall effect points in the other direction. Now, yeah. Now, there was something in the literature, this is called spin anomalous Hall effect. And we are not talking about the spin anomalous Hall effect, I just say this for clarity. Because spin anomalous Hall effect has been discussed in several papers. Here is by Amida, also given by very curvature here. Recent paper in physical materials. And what happens here is that I have this component. I have this sigma y x at z. This again is a time even component. But what happens? It is different if I have my magnetization in this direction or in the other direction. I get a different spin Hall effect. It is the magnetocrystalline anisotropy of the spin Hall effect. So we are talking about another component. Let us do a small symmetry analysis. I start from a non-magnetic material. I have a spin current, and then I have the spin Hall tensor. It is given by this expression where I have the liquid beta tensor here. Then I have just one quantity, spin Hall conductivity. This all the 3 components, they are the same for platinum. Now I go to a ferromagnet. I can look at these 3 quantities again. Now they are not identical anymore because it's the magnetic quantization axis that breaks the symmetry. This is this along with Hall effect. And then you can go to cobalt, where you have the HTP structure, but then again, but we are talking about different components, and there was a very nice this one by Zeeman et al. When you have the magnetization along the z-axis, you can write down the tensors, and they did it, and they found actually that there are components, and they are shown in red here. They are not permitted by symmetry. They said, okay, these components should also exist. There was no calculation. So we have the normal components here, following the ABC, the tensor, time even, and then we have those unusual components. They have actually repeated indices, and they are time reversal odds. So we went to calculate this here for iron, cobalt, and nickel. Now we have 4 effects here: spin Hall effect, orbital Hall effect, and then we have the 2 magnetic components here. We can look at the spin Hall effect here for iron, cobalt, and nickel, and then you see this anisotropy, which is the spin Hall effect. So that really exists there. We can look at the orbital Hall effect, and then you see, okay, the orbital Hall effect here, it is 10 times larger. Roughly, yeah. So the orbital Hall effect is not due to spin-orbit interaction, always larger than spin Hall effect. Then we have now these magnetic components that have not been analyzed much. If we look here, for instance, for iron, then we still, they are of the same size. They are same size. Actually, they also have a field for I'll take a little bit smaller, and also the magnetic orbital is not so involved. I have to say, and this is why this is written here, it depends on the broadening that we do. But what we see here from these calculations, those magnetic effects, they exist, and in theory they exist, and they are sizable. And okay, we can look at the lifetime dependence. So these are the T-even effects, spin Hall effect and orbital Hall effect. And these are the T-odd effects here, because the one on the right hand side, T-odd, it is stemming from a Fermi surface term, and then there is also a kind of very curvature term. But the fact that it is a Fermi surface term there, it makes that if the broadening goes down or the lifetime goes up, I get a big increase of T-odd effects. So they really increase from somewhat over 0 to 4. And you can compare this here to the T-even effects. So the orbital Hall effect, it actually hardly depends on the broadening. But of course, it looks steep here, but if you look at the numbers, it is in the second digit. And here it is a little bit more. So what does this mean? So these magnetic spin, magnetic orbital Hall effects, we predict that they exist, and that actually, if we have very few systems, they are going to be large and important. Now we can look at these are the simple metals, iron, cobalt, nickel, but now we can look at platinum with some top layers where you have a 3D metal on top. So this is our system. Here we have these 16 layers of platinum, and then we have 2 layers nickel, cobalt, copper, or platinum on top of it. And now, in the previous calculation, we had 12. We did not see any spin accumulation or orbital accumulation. But now we have here the interface, and on this side the interface. So we have the spin and the orbital currents, and we have also now the accumulation that we can calculate. And what we do is we take our fields, so actually in plane, actually in this line, but the field is in plane. Then we can again calculate the spin and orbital Hall conductivity, but now also those induced spin and orbital polarizations. And now again, it becomes important. What is the time symmetry? So the conventional one, if you want Rafa-Edelstein spin, Rafa-Edelstein effect, is the T-even effect. But then there is also the one again with repeated in these days that is time reversal form. Okay, so we have now those 2 induced magnetizations, And they point in different directions, as I was showing a few slides back. Now we can calculate from this the torque. So this is the generic expression for torque. Here we do only the spin torque, I have to say, because this is from the exchange field, and the exchange field does not work on the orbital polarization. So we can only work with the spin here for the spin torque. We can work out this expression, and then we see here immediately what kind of symmetry you have in this time equal time is going to determine what your torque is going to be. So we can have from this expression working out the direction of M, working that out, we get either time reversal torque, field like torque, or time reversal even damping like torques. So this is then results here now for the system here. Maybe we start here. So we have there's a yellow curve here. So that is pure 18 layers platinum. So what this is now the layer result in all effects that is large here in the middle. Actually, it approaches the growth value. This is the spin accumulation here. And that is the time reversal even. So this looks like the spin accumulation that also was shown in the previous transparency. And we see a modification at the interval. Now this here is the next column. This is the time reversal or effects here. So the magnetic spin vortex, and you see actually it is only there. I have my magnetic cap layers. It must be in the magnetic. If I take, for example, 16 platinum 2 layers of copper, there is no magnetic effect. It must be the magnetization symmetry, the magnetic time reversal symmetry in those two top layers. And then this is done the time reversal alt magnetic similar to the sign effects. Yeah, and if you look at the signs here, this 50, it is actually not so much smaller than the conventional spin Raspberry Edelstein effect. So these effects, they are new and have to be taken into account also. Now we can also do the step and we look at the orbital polarization and the orbital currents. And here, this is the orbital current conductivity result with respect to the rotator. It is actually quite a bit larger than spin hole conductivity, and it has a different shape. Yeah, what you see here is very flat in the main part of the film, and then actually it drops. Then we can look at the orbital accumulation, and actually the orbital accumulation, then it will be fine. It is again, it is very flat in the middle part, and here actually the effect will be important for the tensioning of the orbital accumulation, but not at the boundary. So here we have sizable orbital accumulation and also on the other side. And again, it depends on what kind of material I'm considering for the cap. These are the two effects that are time reversal alt. So this is the magnetic orbital Hall effect, also only there for cobalt and nickel, and it is the spin accumulation is also there, but there is some time change of sign here. So what do these calculations tell us? That apart from the orbital accumulation is different from the spin accumulation, and the second point is that if I have a magnetic material, I will also have this time reversal alt component. Okay, I will finish now. We can look at if we have our system here, we can look at the torque. But as I said, at this point we do not consider the orbital torque. So we look at the conventional torque where I have the interaction. And we can look at the ratio of the quantities. So this is the time reversal even accumulation, time reversal alt accumulation. And if we go then here to the platinum top layer next to the interface, And this is the torque is dominated by the spin Hall effect. In the next layer here, nickel or cobalt, they are about the same size. If you then go to the top layer here, then the magnetic spin Hall effect actually starts to become larger. But I have to say, this is for a certain lifetime. So it can depend on that, but it is important to take also this the effect of the magnetic spin Hall effect into. Okay, now in connection to the previous talk, I'm
Yeah, for appendix for these panels, appendix for
Yeah, we have plenty of questions. No.
it's a
37.
titanium, so we also calculated.
It's already 20.
But to be honest, I think we did HCP titanium. We did HCP titanium, and this is thin. This is I think this was the 12 layers of titanium that you're looking at here, and this is the orbital part. And what you see here, of course, there are opposite spin and orbital accumulation in titanium. It was inspired by the preprint of Orbital. Here we are at this 2 here, and here we are at 200. So we see really that the orbital accumulation in titanium is a factor of 100 larger than the spin accumulation. However, there is one thing, and that has maybe not been mentioned so much in the previous modeling. What happens is that actually this is the layer that is set. After that, you don't see much anyhow. So it is almost confined to the interface. That is a difference. Even now, it's in view of the time that I have more time, I go back. And when I look here, so this was the spin accumulation in platinum. It is extended and it goes to 0 here in the middle of this 18 layers of platinum. But then if you go to the here, the spin is here also is a possible, but the orbital accumulation is much more concentrated at the surface. And so that is something to take into account, I think, in the future. Okay, so then I can summarize. Maybe I should not have taken out the anti-magnets, but anyhow. So our main point is that there is this magnetic spin Hall effect and magnetic orbital Hall effect, and they are time reversal Hall. They were not considered, and actually no initial calculations, but they are there and they are large and they are predicted for magnetic materials. There was one paper that I had that I knew at the time I was going fast, and there was Timata et al. Nature 2019. They predicted the magnetic Hall effect for manganese 3 tin. So it's a different class of materials. But these are novel effects, and they actually lead to novel thermal effects. Spin nerves, orbital nerves, and magnetic spin nerves and magnetic orbital nerves. And these effects also appear if you go to slab calculations of just non-magnetic materials or with magnetic slab layers. And then they will actually the magnetic time because of all effects they will play a role. As we saw, we have very large orbital Hall effect in the light D metals, so they are ones that are essentially of interest for future orbitronics, and maybe also other effects like this large orbital lens effect. So thank you for your attention.